Section 4.4 is on page 174. Talks about non-homogeneous equations, the method of undetermined coefficients. There are three techniques to use in non-homogeneous equations. We're going to learn two of them. So let y double prime plus p of t of y plus q of 2y, the traditional differential equation. P, Q, and G are continuous functions on open interval. If this doesn't equal 0, then that's a non-homogeneous linear differential equation. The solution of the above equation is given by y. I don't know why they call that y complement. It would have been easier if they would have called it y sub h, the homogeneous. So you find the homogeneous solution, you find the particular correspond to this function, and you add them. So you do those individually. Now, if you want to pick the particular solution, you're going to really look at what is the form of this function g of t. If I see that on the right hand side g of t happen to be an exponential, I let y of p be the general exponential, and I would find a. So if I want to find the complementary coefficients, I need the initial conditions. Particular solutions, you find the coefficients regardless, unless the problem says not to. If I notice that this function g of t happen to be either a sine or a cosine in any combination, I let y equal both, and again you find a and b. And if I notice that this forcing factor g of t happen to be a polynomial, I let y of p be the actual polynomial, and here you would find the coefficients. I called them a, b because I wanted them to fit, and that's how it works. So I want to start a couple of examples really quick. First, I'm going to do two problems, and then I have an example. I want to really point an issue that might happen up if you don't pay attention to it. So I'm looking at page 180, and here we are. So this right here is not 0, which means my solution is going to be y is going to equal the complementary, which is the homogeneous, and the particular. Now the particular specifically in this case is going to be, this is a constant, some letter a. You need to find a. So that's going to be a right there. And the complement, this is a linear differential equation with constant coefficients. We're going to let y equal e to the rt, and y prime will be r e to the rt, and y double prime will be r squared e to the rt. You know what? I'm going to change the format of this. I want to give it its space. I don't want to squish anything. So I'll move this around in a minute. For now, let's just focus on this. There. No need to squish any of this. Let So I'm looking at r squared times e, backwards. I'm looking at e to the rt times r squared plus 2r minus 1 equal to 0. I'm getting e to the rt cannot equal to 0, and it must be that, let me see, that doesn't factor, right? R squared plus 2r plus, again, I have plenty of room. I'm going to really fix this up. Take half of the middle number, which is 1 and squared, that's a 1. So this is r plus 1 squared equaling a 2. R equal negative 1 plus or minus radical 2. So here I know that e to the negative 1 plus radical 2t and e to the negative 1 minus radical 2t work. Well, I would say y equal c1 e to the negative 1 plus radical 2t plus c sub 2 e to the negative 1 minus radical 2t plus my a. But a I could find. A, those I should find. If I take a derivative, it should satisfy this equation still. Y prime is 0, y double prime is 0, right? So if I plug it in, this reads 0 plus 2 times 0 minus a equal 10. So a must be negative 10. So that would be my solution for this differential equation. The only way I could find c sub 1 and c sub 2 if they gave me the initial conditions. Now let me rearrange this and come back and talk a bit about it. Now let me elaborate on what we were talking about just for a sec. Notice this was the general solution was y equals c1 e to the negative 1 plus radical 2 times t plus c sub 2 e to the negative 1 minus radical 2 times t plus a. Now the question is, how come I didn't use this? Took a derivative, a derivative first. How come I didn't take a derivative of that, then another derivative, and plug that in and set them equal? Because we already know any linear combination of those will give me a 0 on the left hand side. So there's no point in me wasting my time and doing all of that work. Again, if you take this, take a derivative of this, take another derivative of that, and if you plug them in, guess what's going to happen? This left side right here is guaranteed to give you a 0 right there, because that's how we got it. And if you're not sure, try that. If I had time, I would, but well, maybe at the end if I have time, I'll do that. But for the particular solution, we find the particular solution, we just use the a. That's much quicker and easier than using the whole thing. Otherwise, the problem becomes chaotic. Well, not chaotic, just becomes too long, right? But when I want to find C1 and C2, I must use the whole thing, all of this, including the particular. And why is that? Because the particular doesn't cancel out. So if I look at number 12 next, let's try that as well. So some students might look at this and say, you know what? Let me find the particular. You're going to say y equal some complementary solution plus a particular solution. Let me find the particular first and get it out of the way. There's a catch to that. I'm going to show you what it is. The particular in this case, what is the general form for a polynomial of second order? At squared plus bt plus c. We use letters A, B, C, D for particular to separate between that and the homogeneous. Homogeneous, we use C sub 1, C sub 2. The book is consistent. We're going to do the same. So if I take one derivative, that would be 2at plus b, and that's about it. So if I take 2 times y, oops, I'm sorry, I'm so stuck on y prime. You guys forgive me, right? X equal x sub c plus x sub p, no big deal. So the derivative equal that. That doesn't look like a derivative anymore. There it is. So if I take this, I'll take 2 times 2at plus b plus x plus at squared plus bt plus c. And that should equal the 3t squared. So if I get the t squares together, at squared plus, if I get the t, I'll have a 4a plus b. And if I get the constants, 2b plus c. And that should equal 3t squared. And from here we know that the number in front of the square must equal the number in front of the square. That means a equal a 3. The number in front of the linear, there's no linear, that means there's a 0. That means 4a plus b must equal 0. Substituting a equal 3 in there, b equals a negative 12. And the constant 2b plus c must equal, there's no constant there, that means a 0, but I know what b is. That means negative 24 plus c equals 0. That means c equals 24. So the particular I got the particular solution to be a, we said a was 3t squared, b minus 12t, c 24 would be the particular solution. What's left? What's left is the homogeneous. I'm gonna let y equal e to the rt, y prime equal, so homogeneous means I'm taking this and setting it equal to 0, really. Oh my goodness. X, right? So 2r e to the rt plus, again, this is separable. I really don't need to use this, but I could if I want, e to the rt into 2r plus 1 equal to 0. E to the rt cannot equal to 0. R equal negative 1/2. So here, the particular solution is a multiple of this. All what I have to do is say c1 e to the negative t over 2. That would be the full solution of this problem. And there's no way of finding c1 without getting initial conditions. So for a particular solution, I could just use the particular part, because if I take a derivative and I plug that in, this will zero out anyways. The next problem I have is an example. On this example, if I said y equal some complementary part, which is what I did in the previous sections, plus some particular part. Well, if you decided to start with the particular, there's a small price that comes up. If you say the particular is multiple of this, that is a e to the negative 2t, take two derivatives, y prime is negative 2a e to the negative 2t, and y double prime is 4a e to the negative 2t. Okay. And if I plug those in there, I will get 4a e to the negative 2t plus 2 times y prime, or plus 3 times. There's y prime, that's negative 2a e to the negative 2t. Why do I keep on squishing things up as if I have no room? Plus 2 times e to the negative 2t equals e to the negative 2t. Well, that's easy. That coefficient must equal the coefficient of a, so let's see. This is 4 minus 6 plus 2, that's 0 equal e to the negative 2t. We have a problem. Exponential can never be 0. What just happened? What happened was, you really didn't pay attention to the complementary first. So let me reverse the steps. What if I found the complementary first? This is, so the complementary, I'm really looking at this equal to 0. I'm gonna let y equal e to the rt, y prime equal r e to the rt, and y double prime equal r squared e to the rt. So e to the rt times r squared plus 3r plus 2 equal to 0. E to the rt can never equal 0. And r plus 2 into r plus 1 equals 0, indicating r equal a negative 2 or a negative 1. Doesn't that mean that this will give you a 0? This will give you a 0? And any linear combinations will give you a 0. So this is c1 e to the negative 2t plus c2 e to the negative t. And do you notice that this right here is included in there, and that's why this didn't work and it will never work? Why is that? Because any multiple of e to the negative 2t is going to give a 0 guaranteed. So, does it matter which order I do those? And yes, it does matter. You should find this first. You find the complementary first. Why is that? You want to know which of those will give a 0? And instead of doing all of this work and wasting all of this time, now I know when I get to the particular solution, I'll say, all right, well, since this doesn't work, I'm going to shrink that and leave it in just for your notes. You really don't need it. But now when I say my particular solution, so I find the particular solution, it is a form of that. That's a e to the negative 2t. And then you look at the homogeneous, you say, wait a minute, that's included. It's right there. So we modify. How do we modify? We multiply by t. That's what we learned when we have repeated roots. So my particular solution is a t e to the negative 2t. So this is called modified. When do you modify? Whenever the particular solution is part of the homogeneous. And now what? Now I'm going to take two derivatives. Well, let's see how this works. Let me move this a bit further down or shrink it up even more. So now if I take a derivative, y prime would be a e to the negative 2t minus 2at e to the negative 2t, and I want a second derivative. Y double prime will be negative 2a e to the negative 2t, and here you'll get negative 2a e to the negative 2t plus 4at e to the negative 2t. Now one thing you're going to notice, too many e to the negative 2t's. When I take this, take e to the negative 2t out, that saves you some pain. That's going to be negative 2a minus 2a plus 4at plus 3 times this plus 3a minus 3 times 2, 6at plus 2 times this plus 2at, and that should equal e to the negative 2t. It should equal that still. So doesn't that mean that I'm looking at, let's see what we have here. We have negative 2a, negative 4a, negative 4a plus 2a, so I'm going to play this along until the end. Negative 4a, that's negative a, and wouldn't this be 6 minus 6? Doesn't that mean that negative a equal 1, which means a is negative 1? So I got it. Put a negative 1 there. So my solution would be y equal c sub 1 e to the negative 2t plus c sub 2 e to the negative t plus or minus t e to the negative 2t. Now, this is a fine answer. The back of the book will combine those. The back of the book will say y equal c1 minus t e to the negative 2t plus c sub 2 e to the negative t. You don't have to do that, but when you see the answer in the back of the book, I just want to make sure you know it's the same thing. Okay, the last aspect of this. They say determine the form of the particular solution, differential equation, do not evaluate. So, if I look at the particular solution in each case, what I really need to do to figure out what this is, the particular solution in this case is the 6th degree. How do you write a 6th degree polynomial? I'm going to use letters a t to the 6 plus b t to the 5 plus c t to the 4th plus dt cubed plus et squared ft plus g, what's up g, that multiplied by e to the 3t so far. Why do I say so far? Because I need to figure out if that is part of the particular solution, the homogeneous solution. So they just want us to list the particular solution, but we have to set this equal to 0 and let y equal e to the rt. Y prime is r e to the rt. Y double prime is r squared e to the rt. E to the rt times r minus 3 squared equal to 0. So we get r equal 3, right? which means e to the 3t, and t e to the 3t is a solution. For this to work, you want to make sure that none of these are there. Do you see that if you multiply this out, this is right there, and do you see that this is right there? So what do? You modify. Do you see when you modify, you must multiply by t squared? And why is that? Because if you multiply by t, this will be gt times 3, which is a common of this. So there's a big difference between me saying I have t to the 6, you have to write the general form of that, versus me modifying, you just multiply by a certain t. So the particular solution would be, actually, I don't want to use that color, that would be at to the 8 plus bt to the 7 plus ct to the 6 plus dt to the 5 plus et to the 4th plus ft cubed plus gt squared times e to the 3t. Now, none of these solutions are in there, and that would be fine. Of course, the fun is not listing this. Listing this is fun. The more fun is actually what? Finding those A, B, C, D. We don't do that. You use matrices. That's where you learn linear algebra. Same deal here. Before I go ahead, let me start with, so far the particular solution is a combination of this. So that's going to be what? A e to the t cosine of t plus b e to the t sine of t. Unless I'm going to let y equal e to the rt for the complementary solution, y prime equal r e to the rt, and y double prime equal r squared e to the rt. E to the rt times r squared, r minus 1 squared, right, if you factor that. So r equal 1. So we have e to the t and t e to the t. Since that's not part of those, that would be the form of the particular solution, and it doesn't need modification. And if I look at the last problem, the same deal happened. I'll take the particular solution, and it's going to be, well, identical to this, except it's e to the negative 3t, so that is at to the 6 plus bt to the 5th. Actually, the beauty of technology. There you go. Now, when I find the complementary solution, I let y equal e to the rt, y prime equal r e to the rt, y double prime equal r squared e to the rt. I'll get e to the rt times, that will be r minus 4 into r plus 3 equal to 0. So r equal 4 or negative 3. E to the 4t and e to the negative 3t. Do you see here it appears only once? I need to get rid of one of those. So how do you modify? Multiply this by just t will do. And that would be beauty. Bingo. Pump those one up, and everybody's happy. That would be to the 7, 6, 5, 4, 3, 2, and a t. And now that doesn't repeat anymore, and there it is. And that would be the final answer, of course. And there is your homework.